Hi, this is Guy Hawkins, and this is a pre-recorded presentation for the 2021 meeting of the Australasian Mathematical Psychology Conference. The title of this talk is Generative Models of Behaviour and Self-Report During Mind Wandering, and it's joint work with Matthias Mittner, Beate Forsman, and Andrew Heathcote. So we often hear terms like mind wandering, distraction, attentional lapses, task-unrelated thoughts, and a range of other terms, but they're all generally referring to this phenomenon that attention fluctuates during goal-directed activity, and often in a way where there's a shift from external stimuli or task-related thoughts to internal stimuli or task-unrelated thoughts. And some reports even put this as occurring up to 50% of our waking hours. And this can be a problem because mind wandering impairs task performance. So we know things like as you mind wander more, you reduce accuracy in things like detection tasks, your response latencies become more variable, and we even see characteristic fluctuations in neural activity. So it's important for us to try and identify when mind wandering is happening so we can try and remedy it and prevent its negative impacts on performers. So how do we measure mind wandering in the lab? Well, it's often with something known as a thought probe. A typical example is shown in the slide. So participants are asked a simple question such as, where was your attention during the previous trial? And this occurs through as an ongoing task is happening. And it's typically responded with some kind of self-report Likert scale, so from on task through to off task. So from a participant's perspective, they're completing some sequence of trials in an experiment. So one after another, these continue, and then at some point it's unpredictable to them. They receive a thought probe, they respond where their attention was focused, and then the task continues until another thought probe occurs at some point in the future. So some properties of thought probes are that they rely on introspection, which isn't itself a problem, but it can make some analysis issues. And they're only measurable on a minority of trials. The ongoing task becomes very different if participants receive too many thought probes. And this means that the responses to thought probes, so trying to predict when people are on task or off task, becomes very difficult when we only have behavioural data. So this is why there's been some interesting choices with how people analyse data with thought probes. So what we typically see is that performance in the primary task is analysed as a function of the thought probe responses. Now this is interesting because it's treating a dependent variable as if it's an independent variable. And this raises at least two problems. A fairly boring one is that it violates assumptions of many statistical tests. But the more interesting one that I'm going to focus on today is that there's no attempt to quantitatively explain how people are cognitively generating thought probe responses. So our approach in this work is to jointly model behaviour and the self-report data. For this, we're going to talk through 4 ingredients that we need to make this approach work. So the first is some mind-wandering data. For this, we're looking at the sustained attention to respond task, or the SART. This is very common in mind-wandering research. It's a go, no-go task that has a very high proportion of go trials, and this induces some pattern of automated responding. So the task setup is extremely simple. Each trial involves a single digit presented to the participant, and it's usually uniformly sampled from the digits 1 to 9 or 0 to 9. And so then we identify one of those digits as a target, so say the digit 3. And if a 3 is shown, you withhold your response. If it's any other digit, you press a button. And participants do this hundreds of times with those thought probes kind of randomly interspersed, perhaps once every 20 or once every 30 trials. A second ingredient is a model of behaviour in the ongoing task. For this, we're going to look at the timed racing diffusion model, or the TRDM. The TRDM is an evidence accumulation-based model that assumes the decision process is made up of 2 components. There's an evidence process that has separate accumulators accruing evidence in favour of a go response or a no-go response, so those are shown on the left here, and those continue until a threshold, and whichever one hits threshold first indicates the response that's given. Either press the button for a go response or withhold and for a no-go response. These 2 accumulators race against a latent timing process, which is related to how people are tracking ongoing time in the task, and they may wish to terminate the decision process without actually accumulating sufficient evidence to an evidence threshold. So one aspect of this model is that when the timing process terminates the decision process, it generates a go response. And our motivation here is that go responses make up about 90% of correct responses in this task. given the setup of the site. And so this is like people knowing that base rate and just use that to emit a go response. Our third ingredient is a model of self-report. And for this, we're using a Thurstonian strengths model, also known as an ordinal probe regression. So in this approach, we assume there's some latent continuum that's related to the amount of attention directed to the primary task. So we have our continuum shown here, where one end is low attention directed to the primary task, so that's off task, or high attention directed to the primary task, and that's on task. And so people will fall somewhere along this continuum. So someone might direct a lot of attention to the primary task, someone else low, someone else moderate, and so on. And so whenever someone is presented with a thought probe, the assumption here is that they take a sample from this distribution, shown with the X. They have some predetermined cuts along this continuum that bin the distribution. And this dictates the probability of a response at the different positions on the continuum. So in this example, the person would give a response for position 3 on the Likert scale. And our final ingredient is a function that links the behavioural and the self-report models. So for this, we're doing a quite simple linking function. So we're assuming that the mean of the latent Thurstonian continuum, so psi, a subscript I is for participant I, is a function of the TRDM parameter for participant I. So I'm just notating this with omega, where this cycles through the 7 freely estimated TRDM parameters. So we fit 7 different models here. And we're going to compare which one provides the best account of the joint behavioural and self-report data. And the key component is this scaling coefficient, beta. So the sign and the magnitude of the estimate for beta defines the association between the TRDM parameter and the mind-wandering continuum. So if someone has a larger value of omega and this beta coefficient is positive, then it suggests they'll have a higher position on that latent Thurstonian continuum. So we estimated 7 different models in a hierarchical Bayesian framework and compared them with DIC. So this table is showing the delta DICs here, where each row is one of those 7 models, where each model was just one of the parameters of the TRDM was tied in that linking function to the mean of the Thurstonian continuum. So the 0 DIC is the best model, the most parsimonious model for these data. So that suggests the evidence rate to incorrectly identify targets to the no-go stimuli, that is, provided the strongest link to self-report data. In the second experiment, we see a difference in that the top model there, so the evidence rate to correctly identify targets, so again, there's no-go stimuli, was by far the best explanation of the data. And so one difference here I didn't mention before is that the number of participants is drastically different between the 2 data sets. And so for this reason, we take as stronger evidence that this top model here provides the best explanation of both data sets when considered as a whole. Now, the model provided a good account of all aspects of the data. So here I'm showing one participant. On the x-axis, we have response times, y-axis, the cumulative probability of response. This data, the dots represent data, and the lines across both axes indicate credible intervals of the posterior predictive distribution, where the vertical placed dots are showing quantiles of the response time distribution. So the model is nicely capturing key features of those data. And that's just one participant, but when we look at all 19 participants in the experiment 1 data, we see a similarly good explanation of the response patterns. We can also look at the goodness of fit for the self-report data. So this is that same single participant here, where the dots are indicating the proportion of times that this participant gave a response for each of those thought probe options on the scale. And the bars are again representing the 95% credible intervals of the model. So the model is doing a pretty good job here, and it does so across the majority of the participants. There's some minor misfits here, but overall we're doing quite well at capturing the self-report data through that linking function. Now, the psychological interpretation of the DIC preferred model is that the latent mind-wandering continuum is linked to the evidence rate for correctly identifying targets. And so the scaling coefficient here, that beta parameter, has estimates that are negative, which suggests that participants who are more sensitive to no-go stimuli were less likely to self-report mind-wandering during the task. So in one sense, we might say, well, that seems pretty obvious. And so who cares with all this effort of a joint model? Well, I'd argue that one reason this matters is that response variability has been taken as a robust behavioural marker of mind-wandering. And the literature has interpreted this as an outcome of more variable processing of the evidence. However, it's rarely, if ever, modeled. And so it's basically a conclusion from intuition that if responses are variable, processing must have been variable. And the problem is that intuitive qualitative predictions are not necessarily unique. So a low versus a high drift rate generates more variable responses, and that's the model that was preferred by DIC. And a high versus low processing variability generates more variable responses. That's a model that was tested here, but was very much unfavored by DIC. So we've shown here that modeling the joint distribution of choices, RTs, and self-report data provides a finer grained tool to investigate associations between cognitive processes. Thanks for your attention.